give you a first image of what kind of thing you can oh, please, kill the damn things, please. Just kill them. You know?
Kill them. Okay,
You
here.
have a gun?
Like, kill them sweetly. Yeah, turn the laptops off.
Oh.
I can download them. I stop you.
So I have to do an entire lecture with an apple looking at me? Okay. Well, so what we'll do now is I'll try to give you an introduction to logic programming with a programming language that has been my research for the last couple of years. So, now, let's begin by taking a step back. Consider a lot of concepts that you might imagine to be primitive and obvious. Okay? So consider something like you would never feel the need to explain. Like natural numbers. I mean, are natural numbers something that is complex? 3 and 5. Complex concepts. 3 plus 5, is that a complex concept? 3 plus 5, in the most cases, should be reasonably intuitive. It should be obvious. Now, think about an if in a programming language, in Java, in C#, in C, doesn't matter. How many of you here consider if complex? I mean,
I don't know, please.
so the point is, it is not. And why is it not? Because we give it for granted. As we do stuff more and more and more in one very specific way, at some point it becomes almost a part of us. So the intuition of that becomes so deeply ingrained that we assume that is a primitive concept and it doesn't need further explaining. So in this course, what we do is we challenge the very assumption that there are primitive concepts. So what I'll tell you is that integers, ifs, whiles, most of the things that you are used to are not actually primitives. What we will do is we will start with some bare bones, so-called logical operators. Now logical operators are some thingies with some rules that we can use, and we can actually even use it in the very practice of implementing a program on a computer and then running it, so not only using the mathematical sense of a whiteboard, but actually use it on a computer, to define from scratch a lot of concepts that otherwise you would think are primitive concepts. But if we can implement them with some concepts that are even more basic, then they were not primitive concepts at all. The result is that we will rediscover how concepts that we thought were basic, like an if in a programming language, are actually not basic. And we will be able to redefine them precisely as we know them. There is not much use in redefining an if then else in a modern programming language because it is well known, but what we will be able to do is recompose them also in new forms. So who's to say that there does not exist an alternative formulation of if then else in some other format, obviously not just if then else too, that has some new meaning. For example, defining new programming languages that work in completely different ways than how we usually think in terms of programming languages. During the course, what we will do, I will actually offer all these slides, so every Monday I will do another one of these, but in another classroom for those that are interested. So this is not forced on everyone that takes part in the minor. So we will introduce informal logical reasoning and introduce the logic programming language that we will be using and its internal mechanisms. So today we stop here. Then we will define Boolean expressions, which I find kind of funny because Boolean expressions are considered a form of logic, but we redefine the simplest form of logic within the framework of logic itself. I mean, recursion is always fun.
Recursion is its own reward.
And then we will define natural numbers with logic. So we wouldn't in principle even need something like hardware integers, which we will keep using because after we define natural numbers then we'll go back immediately to using hardware integers because they're like a million times faster, but in principle we would not need them. Then we'll build complex data structures like lists, binary trees, and even balanced binary trees. Finally, we'll build a small programming language entirely from scratch with variables, ifs, whiles, and fors. Yeah, I mean, within the scope of a lecture, this is more than enough. And then I'll try to point out a possible extension of the use of logic to discuss fragments of computability. So what can logic do, and also what can logic not do, which I find to be a very fascinating topic. After this lecture here, you should be able to get working on building your own programming languages. So today we will introduce logical reasoning, an intuition of logical processes, and finally we'll show a fragment of the Boolean expressions example to see how it works in practice. So, now, the basic rules of logic are actually very, very simple. So logic is just a way to transform and manipulate sentences made up of symbols. Seriously. So, what you do is you have a bunch of symbols, and you have a logical rule that tells you, you have these symbols, oh good, now you have these other symbols, and then you go on. Okay? This is in a nutshell what it is. Now these symbols are usually common signs such as numbers, letters, Greek letters, etc. But we can use whatever symbol we want. So if you take a look at mathematics, then in mathematics there are plenty of very funny symbols everywhere. So we can use them. We can use whatever we want. So indeed, in the first example, we will use smileys and other icons as symbols, just to show that we are not forced in any way to use traditional symbols. So this is important. If you see something like 0 somewhere, within the framework of logic, it is not guaranteed that 0 means what you think 0 means. So if you look at your logical definition, the way things behave defines what they are, not otherwise. So the symbols themselves mean nothing. Or as they say often in the books of Game of Thrones, woorden zijn wind. Because most people in the books are very untrustworthy. So, yes. So the type of symbols you find mean nothing. But what we do that give them meaning is that we define rules which transform series of symbols. The way the transformation happens allows us to attach a meaning to these symbols. Okay? So, after defining symbols and rules, we can actually use our logical system to process information. So we start with a given proposition, which is the input. It is like the input program of the whole process. And the input proposition is just a series of symbols. Just like literally a sentence. You know a sentence? Think of a sentence. Like this is a sentence. We have the symbols. This is a sentence. It is a sequence of symbols.
You have to split those words, right?
You can even have more fun and you can say yes, T-H-I-S space, I-S space, etc. So yes, everything we do is just sequences of symbols, but even a programming language is a sequence of symbols. It really is. And, oh yes, this would also be a sequence of symbols. 3 plus 2 equals 5. 3 plus 2 equals 5. 5 symbols. Oh, cute. Or smiley, smiley, candle, candle. Yes, this is a sequence of symbols. Then we have our rules that transform stuff, and we keep applying rules to our proposition, which may be this or something else, until we reach the final answer. Or the process is stuck and cannot go further. Now, when the process is stuck, it means that the initial sentence could not give you a final answer. It throws an exception or throws a segmentation fault. So not every time all the rules of the dynamics of your thing can actually lead to a reasonable result, right? You know a program that throws an exception and dies? Has that ever happened to any of you here? Never. Okay, so let's begin with this example. The symbols of our language are a smiley, a candle, a tree, and a coffee cup. So a proposition is accepted, is true, in our system, if and only if we can process it until we reach a coffee cup. The idea is that coffee cups have a very prominent role within the lives of mathematicians and programmers, so what we always want to get is a coffee cup. Okay?
Wouldn't you rather have a filled coffee cup?
A what?
A filled coffee
A filled coffee cup. Yeah, what? Oh, this is not bacon.
cup. I was hoping for bacon.
So, our rules, which we begin with an informal expression of these rules, are this is G0. G means ground, so you reach the ground, you're done. A coffee cup means we are done. 2 smileys followed by a 3, and then further followed by a bunch of symbols which we call R, means that we will have to process R to find the answer. So if we find 2 faces and a 3, followed by a bunch of things, we delete the faces and the 3, we take the remaining thing, and we just go on with the remaining thing. Got it? So we cut away the first 3 symbols if the first 3 symbols are.
Smiley, smiley,
Thank you very much. If we find candle, candle 3, we cut it off and we go on with the rest. Okay? Right? What does this mean? Nothing whatsoever. Just a logical process. A logical process doesn't necessarily have an intuitive understanding. So, let's begin with smiley, smiley 3, candle, candle 3, smiley, smiley 3, coffee. So what do? Step 1, we use the last rule. So we had smiley, smiley 3. Remember? Let's go back. Oh, sorry, that's R1, smiley, smiley 3, we cut it off. And candle, candle 3 then. So, smiley, smiley 3, cut it off. So you see, candle, candle, 3, smiley, smiley, 3, coffee.
Done.
Yes, but let's follow the rules. Then, next rule, candle, candle 3, off. Smiley, smiley, 3, coffee. Then, smiley, smiley 3, go away. You see? This is a computational process in the sense that it is so simple that at some point it even becomes boring to watch, and you could, I don't know, build a machine that runs it, or implement a program that runs it, okay? If you can specify it in the form of very simple logic with these very obvious steps that you can follow very intuitively without even thinking, this is the bit. You just find a rule and apply it. You don't need to think about it. This is a logical process. This is the strongest feeling that you can have for a logical process. So now we have the coffee cup. We are done. The proposition, this proposition here, was a true proposition. It was an acceptable proposition. A proposition that doesn't crash and burn miserably. Now let's consider something else. Smiley, smiley 3, smiley, smiley 3, candle 3, coffee cup. First rule, yes, we can apply. We take off the first. Second, we cut off the second 3 symbols. And now, can we apply any rules? We have no coffee directly, so we're not done. We have no candle, candle 3, because we have candle 3. And we have no smiley, smiley 3. You see? But we are stuck. We cannot apply any of our 3 rules. So, this proposition was a false proposition. It is a not acceptable proposition in our system. Okay? Good. This was not very formal, but hopefully intuitive enough. Now, in this section we will present a more formal treatment of inference systems. So we will see how we can do the very same or a similar thing to what we just did, but without having to use words. Just with symbols, with a clear meaning. We shall give a clearer syntax and semantics of symbols and rules. So we specify exactly how you would define your symbols, how you would define rules. We will use a formalism, which is also a programming language, which I called Meta Casanova. For the history of the name, you may come later to me, and I'll gladly share it. You can download it from here, the sources. Otherwise, in the GitHub of the SedMiner, you will find the zip of the release of the metacompiler. Now, you still with me? Still following? Do you want me to go on? Oh, okay. Good. So, we have 2 types of symbols in Meta Casanova. We have data symbols which we use to store and structure information. So data symbols are information containers. Then we have function symbols, which are used to specify where information is transformed. So the names have been kept as typical names, so data to define. Data, functions to define.
Function.
Yes, exactly. Thanks. So, data symbols are the ones we use to assemble most of propositions, which we also call expressions. And propositions are nested sequences of symbols. And nesting is defined by either the priority of symbols or parentheses. Now what this means is that if you have an expression like 3 plus 5 times 2, what this actually is an addition of 3 on one hand and 5 times 2 on the other, because times has higher priority than plus, right? So if you have 3 plus 5 times 2, they are not 5 symbols, they're actually a tree of symbols. I should be able to draw this. Not connected. Do you see a marker anywhere? Does anyone have a marker? Okay, doesn't matter, doesn't matter. Okay, so let's take 3 plus 5 times 2, okay? Which is clearly a sequence of symbols. It looks like a sequence of symbols. But what this actually is rather something like an addition of, on one hand 3, and on the other hand, what is on the other hand?
5 times 2.
Times. Just times. Times of 5. 2. Right? This came out surprisingly nice. You see, so basically, when I give you this, what this is a single thing. It's a plus. It's a plus symbol. Plus symbol requires something on the left and something on the right. What's on the left? 3. What's on the right?
Times.
A times. But times require 2 symbols, one on the left, one on the right. What is on the left?
5.
And what is on the right?
2.
You see? So actually, this is what we mean by... excitement. This is what we mean by a nested sequence of symbols. Because actually it's not just a linear list, but it has internal structure, internal hierarchy. And, well, how do we define nesting? Either by priority, so what I just did was I know that times has a higher priority than plus, so times happens first. So times happens more lower in the higher in the tree. Or I could put parentheses by hand. So you know that if I wrote, this would not be the same as the one above, right? Ah, yes. The guy, I see the cranes. You see, this is not the same thing as above. So if we put parentheses, then we actually change the order of nesting. Okay. So this is the simplest way to define a data declaration, to define a new symbol, a new data symbol. So data, name. You know, you're not always going to write name here. But depending on the symbol, you might you might actually write something else. This could be anything. This could be customer. This could be 0. This could be plus. Whatever. Does it matter what you call it? You could call it ZXXY. It's going to be hard to imagine what the hell you meant, but you can do whatever you want. Then 2 points and type. And here you say that this symbol here has this type. You know what a type is, right? So what you're saying is, I have a type, like people represent people, and I say John, semicolon, sorry, colon, person. So John is a person. Okay? Yeah, okay. So we can use now the John whenever a person is expected. If we say John is a person, and whenever we expect a person, we can put John there. Okay? Or Kees, since we are in the Netherlands. What would be the most common Dutch name? Kees? Jan?
Yeah.
Jan.
Jan?
Yeah,
Okay. Okay, so here is a concrete example. Now this is an example that actually compiles. I want to define true and false. True is an expression, and false is an expression. Now here I'm saying expression. Perhaps it would be better in this example to call this bool expr, because I want to define Boolean expressions. Okay, so whenever I write expression here in these slides, I'm talking about Boolean expressions, but since we are defining Boolean expressions, I shorten this to Boolean to exp. But this should be bool exp. So true is one of our expressions. False is one of our expressions. Now, okay, so data symbols are not always so vanilla. In some cases, a data symbol could have another syntax. So data, P1, arrow, P2, arrow, P3, etc. until Pn minus 1. Then the name, then Pn through Pn plus n. Oh, this is a mistake. And this says type. Now, this means that this symbol, to be used, needs a bunch of things to the left and a bunch of things to the right. So you cannot just use it alone. You need stuff to the left, stuff to the right. An example is better than 1,000 words. Or the vertical bar, which I'm going to use for logical OR. But how do I use logical OR in Boolean logic? I need something to the left and something to the right. Does this match your experience?
Yes, of course.
Yes, no, I would seriously like a neck from everyone.
Yes.
Okay, so, and what is on the left? Is it an integer here?
Boolean.
No, it is a Boolean?
True, false.
No,
Expression.
it's a Boolean expression.
It
I mean, you
be
could-
Boolean as well, right?
Yes,
You could put in true as well.
you could put in true as well, but you could also put
False.
true or false,
Yeah, of course.
which would be a composite expression, right? So what we say is that first we want an expression, then an OR, then an expression, and when you have all these things together, then what do you get?
You get an expression.
You get an expression, right? Because the whole OR of two Boolean expressions is a Boolean expression, yes. Good. So, now these are all things that we could write. True or true is a valid proposition. True or false is a valid proposition. False or true is a valid proposition. False or false is a valid proposition. But also, true or false. That is also a valid proposition. Yes? So we have just defined this. Now, associativity is by default to the right, so if you do not put parentheses, like this, what the system understands is this. So it puts the parentheses to the right. Okay? Because OR only accepts two things. So this is considered the first OR, and this is considered the second, by default. After the declaration, you could say associativity left to switch this behavior. Okay? So sometimes you want the parentheses to be put leftmost. Now, you have written compilers, right?
Sort of.
You should notice a difference in the length it takes here. So this would be like 50 lines of Lexer and parse. Now, suppose we now want to define the other very common operator, so AND. What do we want for AND? Well, an expression, a Boolean expression to the left, a Boolean expression to the right, and this whole thing becomes an expression. Now, there is a bit of ambiguity now, because we could say something like true and false or true. Which one of these is going to happen? Is this true and false or true true and false or true?
The first one?
First one.
No, we don't know. Never make an assumption unless it's specified.
Well, the associative.
Yes, associativity is to the right, absolutely. And which one would be correct?
First one.
first one?
No. Because AND has higher priority than OR. Because AND behaves like it's logical multiplication. So actually this is what we would like, but this is what we get. I didn't realize actually that the example also allows this thing that you also do not want first. So what you can do is you can specify a priority of the symbols. So after the definition you can say priority 10 and priority 20, and all of a sudden AND will win. So if you have a sequence of ANDs and ORs, then the ANDs will win. Okay, so we have defined true and false as expressions. But, I mean, are true and false really Boolean expressions?
They're data.
Yeah, but
Ourselves.
they're values. True and false are values, not expressions. An expression is usually something composite. So something else we can do is that we would like to say that true and false are values because they are values, not expressions. An expression is something more complicated. But we also want to say, okay, but true and false can also be used as expressions. They are values, but they can be used as expressions. So we can redefine true and false as values. And now we've broken the whole thing. Because if we just leave it like this, then this is not acceptable anymore, because OR expects expression, but now we just said that these are value, which is not expression. But what we say now is value is expression. So any value is also an expression, which is a form of polymorphism. Okay. So now any proposition of type value that is only true and false will be allowed whenever a proposition of type expression is also expected. Okay? How long have we been going? Am I going too fast?
Faster.
Faster! It can! Should it?
No.
Oh, okay. Now, the second thing that we can define are function symbols. Now, function symbols are used to define the transformations themselves. They start from a bunch of input propositions made up of data terms, and what they give us is another bunch, another proposition, so other data terms, with intermediate recursive steps. So, to define a function, we actually have two steps. The first one is we declare the function. So, the name, the parameters, and the type. The second one is we define how the function behaves as a series of rules, which are defined recursively. So, this is how we declare a function. A function can have parameters to the left and to the right. We have a bunch of parameters to the left. Then we have the name. Then we have a bunch of parameters to the right. The last arrow is a mistake. And then, yeah, guess why? And the most important bit is this. This goes, returns, a value of return type. So now we have just defined Boolean expressions. What would we like to do with Boolean expressions?
Turn them into values.
Turn them into values. I give you a Boolean expression, and you give me back, and the value is going to be true or false. So, oh, wait a second. Oh, okay. I should have emphasized this a bit more. So this is the function definition. Func eval stands for takes an expression. Then this means that eval of an expression is also an expression itself. This is for advanced usages, so just, you can also put nothing here. Goes into value. So the most important bits are this and this. Eval of an expression returns a value. Valid uses of the function would be eval true, eval false. Well, eval expects, we said, an expression, but what did we just give it? A value. But what did we also say about values? They are also expressions, so this is valid. This is also valid, but this is trivially valid because, well, this is an OR of two expressions. Two values actually, but values are expressions. But this whole thing is an expression, which is precisely what eval expects. And so on. Now, what we have specified so far is what kind of shapes are acceptable for propositions and function calls. But this doesn't say anything yet about how computations happen. So how do we take one of those and actually say that eval true is going to be true, eval false is going to be false, eval true or false is going to be true, and so on. So this we still have to specify, right? So the evaluation of functions is based on rules. Now rules are syntactically quite simple and hopefully the weirdest thing you've ever seen running on a computer. If it isn't, I will be personally disappointed. Now, there are only two operators that make up the whole language. This whole programming language is made up of these two operators. The horizontal bar, you can make it as long as you want, as long as it's at least two stripes. And then the arrow. This is not a joke, this is the syntax of the thing. So, the horizontal bar and the arrow can both of them be read out as therefore. They both capture indeed implications. So, as in, if A is true, then B is also true. And the arrow specifies implication at a smaller scale, so from function to result. The bar specifies implication at the larger scale of you have input, you have a bunch of steps, you have an output. That's what you use the bar for. This is roughly what a rule is going to look like. We have here the function input and output. Here we have a bunch of steps, of intermediate steps. And both, these we call the main proposition, this we call the premises. Premises, voorwaarden. Okay? So all of these have to happen correctly for this to be true. Okay? So this is in the sense in which this is an implication. If these are true, then this is true. Okay? The premises and the main proposition are all defined in terms of this arrow here. On the left of the arrow, we have the input proposition. On the right, we have the output proposition. And it looks like this. Input symbols, arrow, output symbols. So concretely, what you will actually write in a rule will look like this. I1 goes into O1, I2 goes into O2, etc. for n times. And under the line, the bar, you have input goes into output. Now this is the main input of the whole rule. This is where we start. Okay? Then we follow the premises, and then we go to the output. Okay? Is this weird enough?
Yeah.
Needs to be bigger.
Sorry?
It needs to be bigger.
Yeah. If you have any suggestions.
Which line?
What might be surprising, this I can promise, and we'll see how this is true, is that this way of writing things is as powerful as Java. To the point that you can build whole of Java here.
It's crazy.
Would anyone want to bet against this? Oh, come on! Okay, but you wouldn't believe it, right? Come on, they are way too far. They are too far, Java in this.
Well, no.
Oh yeah, come on.
They're both lovely.
Java to one extent. But, so, we just saw this. Now, let's go to an example. This is a concrete example of a rule. Eval, true, implies true. Right? When you have eval true, what is the result of this? True, right? This makes perfect sense. And there is a bar, but there is nothing above because as soon as we get this input, we don't need to do anything else. If we find this input, then what is the output?
True.
Simply true, right? Does this still make sense? Okay. Now, so the rule that we just saw looks for an input of shape eval true, and the moment this input is found, we immediately, directly return true. Now, its sister, we find eval false. What do we give back? Do we need to do anything?
No, just give back false.
We just give false back, right? Now, okay, sometimes the rule is more complex and we cannot always immediately determine the results directly from the input. So sometimes we have an input that is so complex that we can't directly give the result. For example, a case where the input would be more complex in our example.
True or false?
True or false. You actually need to do something more than just look at the input. So in this case, we actually have some premises. Let's take this example. When we find eval of A or B, do not look at this yet. So we find this, okay, eval of A or B. We cannot possibly specify all possible A's and all possible B's, or can we?
We can.
How many are there?
Four.
Four. How many possible things can we have left and right of an OR operator? Sorry? Infinite. Yes, we have infinite combinations. We can have an OR of, how long of an expression? It doesn't matter. It can be an expression of five things, of 1, of 50, of 50,000, of 50 million. I mean, obviously at some point it will not be representable anymore on the machine. The point is, we don't know. And we also couldn't list 4 billion possibilities here for, once again, obvious reasons. So what we say is, okay, we find OR with A and B. But what is A and what is B?
Expressions.
Expressions. What for expressions specifically?
Boolean expression.
More than this, can we say?
True or false?
That seems to be excessive already. They could be true or false. Yes, so A could be true. A could be false. A could also be true or false. Or true and false. Or true or true or true or true or false. A could be true or false or true or false or true or true or false.
You could also input 5 times 2 or false.
No, you could not.
Well, yeah, but you get an error.
Oh!
Hopefully.
But so, you see, we don't know what A is. A is a Boolean expression. Which one? Any Boolean expression. We don't know anything, how long, how complex is it going to be. We don't know anything, we can't say anything. But, what we can say is that we have eval A or B. We can't solve it directly, but what we can say is that, okay, now, check eval A. Right? And eval A will eventually give us
True or false?
or false. But in this case, what are we saying? What do you think happens if eval A tells us false?
Nothing.
This rule doesn't apply.
That this rule doesn't apply. So this specific rule stops. It doesn't have an answer for us. So it stops. It doesn't cause an error. It just says to the system, no, I can't do anything here. But if eval A is indeed true, then what do?
Return true.
We return true at the end. Okay? You do also know, do you recognize the fact that this is how an OR is supposed to work?
Yeah.
Because if the first side of the OR is true, we need to check the right hand side.
No.
No. Whatever the other side is, if the other side is true, then it's true or true.
Then it will be
Depends
or
on
else.
if you put, if you say the right side or left side.
Yes, but okay, you could also do this with B, obviously. It depends on how you formulate other rules. But the point is, if the left side has a value of true,
Then it's
then the right hand side is irrelevant. If the right hand side comes out true, then what you had really was true or true, which is true. If the right hand side is false, then you had true or false, which is
True.
still true. Now, oh yeah, okay. Now, if eval A evaluates to false, indeed, we simply look for another rule that can give us an answer. Right. Oh, this slide just floated like 10 slides after. So this is the other rule. Look, eval A or B. So the entrance is the same. We have an OR of two expressions, A or B. What we do is we start with eval A, and what do we expect So if we get true, is this rule going to do anything?
It goes to the next.
Sorry?
It goes to the next.
Yeah, it goes to another rule. It stops. This rule here, if eval A tells us true, this rule stops. If eval A is false, then what do?
We evaluate B.
We evaluate B. Because A is false, so we check the other side of the OR, which is B. What does this give us?
Why?
Y. What does Y mean in this case?
Well,
Yeah,
Or
this
no.
expression.
No, this is just a variable. So whatever eval B gives us, we don't care. We call it Y, and we give it out.
So you could also put B there.
No, because otherwise it would shadow this B. So it needs to be something that is neither A nor B. It could be C, or D, or result. Yeah, or B prime. So the idea is that if the left-hand side A is false, then if the right-hand side is false, then the whole order will be false, because you have false and false. If A is false and B is true, then it is true. So the whole A or B, if you know that A is false, is always going to be equal to whatever value B had. Got it or not? Okay. Oh, this is the long explanation. The idea is that I would recommend you to go and take a careful reading of the slides afterwards.
But you can also say the last here, leave the second rule out and say eval A B is B. If eval A is false.
Oh, put here instead of Y?
Yeah, and
No,
eval B
that you
is-
cannot do.
No, eval B is I, leave it away.
No, you can't.
Oh.
Because you really need to evaluate B to know exactly what B returns. Whatever the evaluation of B returns, Y is what we need to give back. So this actually tells us something. Even if we don't know precisely what this is, it doesn't matter. Whatever this was,
So that rule you can't leave away eval
No.
B. Right?
because otherwise this Y is undefined.
Yeah, but put B there.
No. No, because B is an expression.
Okay.
Ah, let's see if we can find it. Oh no. Because of this. B was an expression. But what we need to return is a value. So we couldn't just return B, because B could be an expression like true or true or false. But what we really need to return is a single value, like either true or false. Okay? Okay. So, now the last thing that we still have to specify is how are rules selected. So we have a bunch of rules. Together they cover the whole execution of the program. Now we actually need something more. Because the rules are just a library of possible evaluations. But which specific rules will be selected and in which order? We miss the initial input. This input will, recursively, determine which rules are selected in which order. And the process either finds an output or it gets stuck with no answer and it throws an error saying, no, for this input I could not find a meaningful answer. So, let's take a look at the whole process in action. Oh, this is a recap of the whole thing. Now take 2 minutes and read this carefully, line by line, please.
die nou logisch is het wel anders in logisch.
May I go forward? Sorry? Should I? Okay. Now, so this is the whole definition, but this is not yet a program. This is a way to execute a program. You could also imagine this as kind of a way to specify a virtual machine. Rules for computation, but not yet any call, any entry. We are missing an entry point, essentially. So, let's suppose an initial input that the metacompiler accepts separately, which is eval false or true. This takes the name of the current proposition. It is the thing, the proposition we are currently processing. The first step is to find which rules match the current proposition. The rules that match it could be used to evaluate the current proposition. So, eval false or true. Now, which one of these 4 rules could be used? The second,
The last two.
yeah, for eval false or true.
Oh, okay. Only the
Eval
last.
A or
Last two.
eval A.
The last 2.
Yeah.
Do not think about the fact that you already know the answer.
Okay.
Think about, imagine, you don't know the answer, and you have to find the answer through these things. So what you do is, you check which rules match. Now, you have eval, false or true. Is false or true equal to true? No, it isn't. It will eventually give us true, but remember, here is the thing I said before. The meaning of symbols is nothing. The only meaning we have is how you compute stuff with the arrows. There is no other meaning. Just because I wrote...
It doesn't know anything.
It doesn't know yet, so we have to verify that it's going to give the right result. So once again, is false or true equal to true? No, they're different expressions. One is an or, and this is just true. Got it? Is false or true equal to false? No, because you have false, which is just a constant, a value, on one side, and an or, which is a complex expression, on the other. Is false or true equal to A or B?
Yes.
Yes, as long as A is equal to
True. False.
false and B is equal to.
True.
Is false or true equal to A or B? Yes, as long as A is equal to false and B is equal to true. So we have 2 rules, these 2, that might be used to solve eval false or true, right? Which one of these 2 will actually provide the answer? We don't know. So, but we have found the matching rules. So these 2 are the rules that match our expression. So these were the candidates. We just checked the input of the rules to see if what we have, the current expression, matches the input somehow. This is how you actually do it. You can write the input of a rule, this is the input of the first, right above the current expression. And you check. Now eval matches, but this doesn't match. This is the same intuitive process we just ran. For false, once again, doesn't match. For A or B, you see, if you can write it like this, you see, just by putting spaces and parentheses, what you clearly see is that A is false, B is true, and then the 2 things are the same. Does everyone really get it? Okay. And so the second rule matches, so as long as A is equal to false and B is equal to true. Now, A is equal to false and B is equal to true is called a binding of the rule variables. So we